we're going to be doing inverse functions. Now if you think back, we've talked about relations and how relations are a mapping. So if I have my domain over here, my input values, and my range, which is my output values, and I'm going to have a rule. So I'm going to use y is equal to 2x plus 3. Well, now if I pick an input value of 4, when I plug this into my function, I would have 2 times 4 is 8, plus 3 would give me an 11. So in my range, I have this 11, and my function maps my 4 to my 11. I could pick 0 to be in my domain. When I plug it over here into my function, 2 times 0 would give me a 0. Add it to 3, that would give me a 3 back for my range. So 0 would be mapped to 3. I could do that with just about any number I wanted. I could put a 1 in here, and that would map me to a 5. So a relation is just a mapping of points to each other. So 4 gets mapped onto 11, 0 gets mapped onto 3, 1 got mapped onto 5. Now when we talk about inverses, an inverse is what would map our range back to our domain. So for this particular example, if I wanted to look for the inverse, I would have to ask myself, what would map this 5 back to the 1? What would map this 3 back to 0? And what would map this 11 back to 4? So as you can see, the range of our original, these values right here, the 11, the 3, and the 5, become the domain of my inverse, and vice versa. The domain of my original now becomes the range of my inverse. So when we're talking about inverses, we are basically undoing our original mapping. Now in order to find your inverse, there's 2 things we have to do. First thing is we need to solve it for x, or whatever variable might be used for that particular problem. And then the second thing we need to do is switch our x and y's if it's appropriate. So if I come back to this example here, it says the first thing I need to do is solve for x. Well, in order to solve this equation right here for x, I'm going to have to subtract 3. So I would have y minus 3. Then divide by 2. So I need to divide this entire equation by 2. And I end up with 1/2 y minus 3/2 is equal to x. Now this right here is the inverse of that equation. So remember function notation? We could have also called this f of x because I have a function in terms of my variable x. If we leave our inverse like this, we would also call it f inverse, and then this particular one would be y. Now this little -1 is not an exponent, it's a notation. So this just means the inverse of f, and right now I've left my variable to y. Well, the second thing I told you to do when you're doing the inverses was to flip-flop your x's and your y's. So I could rewrite this as 1/2 x minus 3/2 is equal to y. And if that were the case, then I would write it as f inverse of x. There should be an x there, it's not staying. The reason it would now be an x over here is because the variable I've used in x is x. What you have to realize is that you can switch the variables if they don't actually have a meaning, like as far as a story problem goes, because it's more standard to have our equation written in x. But what you have to realize is that for our inverse, the x values are the old y values. But this is kind of the standard way to write it. So this would be f inverse of x, and then we have our equation here. So here's another example. We want to find the inverse of 3x squared plus 2. Well, now remember, f of x is just another name for y. It means our function in terms of x. And the first thing I need to do is to solve it for x. So I need to subtract 2, divide by 3, and now to get rid of that square, I need to square root both sides. But remember, since I'm applying the square root and it's an even root, I have to have the plus minus. So for this particular one, I would end up with x is equal to plus or minus the square root of y minus 2 divided by 3. Second thing says to switch the x and y's. Well, right now my x and y's have no specific meaning as far as a story problem goes, so I would go ahead and rewrite this as y equals plus or minus the square root of x minus 2 over 3. I'm not going to worry about rationalizing this particular problem right now. If I want to put it in function notation, in inverse notation, I would have f inverse x is equal to plus or minus the square root of x minus 2 over 3. And that would be my inverse in terms of x. But what you have to remember is that these x values, these input values, are the old output values. Now we're going to look at the graph of a function and its inverse. I'm going to start by graphing f of x equals 2x plus 4. So I need to come up here to 4, that's my y-intercept. My slope is 2, so I go up 2 over 1, or down 2 back 1. And here's my graph. Okay, when I do the inverse, first thing I need to do is solve it for x. So I need to subtract 4, and then divide by 2. And I'm going to go ahead and simplify that. So I would have 1/2 y minus 2 is equal to x. Then I need to switch my x and my y's. So I would have 1/2 x minus 2 is equal to my inverse. When I go to graph that, I want to start down here at -2 for my intercept. And then my slope is 1/2, so I go up 1 over 2. And I get my inverse. So now what we need to do is we need to look at our inverses. And one thing you might notice is that they look kind of similar, but they're going off in kind of the opposite directions. Well, what I'm going to do is I'm going to graph the line y equals x, which goes right through our origin, just like that. And if you remember from geometry how to do reflections, what happens is when we do inverses, our inverse is a reflection of our regular one over the line y equals x. So if you were to draw the perpendicular lines, these two distances would be the same. Which should make sense because remember, for our original we had the points x and y. So when x was equal to 0 for our original, y was equal to 4. When we come down and look at our inverses and we look at the points x, y, we have to think, well, we need to flip-flop our original points around. So my x value of 4 should give me back a 0. And as you can see from our graph, it does. So they flip their x and their y's. Now one thing to consider is that if the inverse and the original equations are both functions, so if they both pass that vertical line test, then they're called inverse functions. Otherwise, we just call them inverse relations if they don't pass the vertical line test. There's a simpler way that you can tell whether or not an inverse is going to be a function, and it has to do with this idea of reflecting it over the line y equals x. And what happens is basically your graph is rotated 90 degrees downward. Well, if we take our original and we look at the vertical line test, so it passes the vertical line test. When you have a vertical line and you rotate it 90 degrees, you get a horizontal line. So what you can do is you can look at your original, just your original graph here, and if it passes the vertical line test and the horizontal line test, which means a horizontal line passed anywhere would only hit one spot on your graph, then you know its inverse is going to be a function also. Next thing we're going to look at is how can you check for inverses? Well, one neat thing about inverses is that if you take the compositions, so if I do f of g of x and g of f of x, and they both equal x, then they are inverses of each other. So here's an example. I have f of x is equal to 2x plus 4, and g of x is equal to 1/2 x plus 2. It wants us to use compositions to check if they're inverses. So I'm going to start with f of g of x first. Now remember, when I do compositions, I take my function on the outside here, so the f function. I'm going to write it with an empty set of parentheses wherever I have an x. That way I'm less likely to make a mistake. Then I'm going to go plug the g function in. So this function right here, my g function, gets put in that empty set of parentheses. Then I go ahead and simplify it out, distribute the 2, and I end up with x plus 4 plus 4. So that would give me x plus 8. I can stop right there actually, because in order to be compositions, both f of g of x and g of f of x have to equal x, and my first composition failed. So this one is no, they are not inverses of each other because I didn't get just an x here. Okay, let's try the second one. So I've got f of x is 4x minus 12 and g of x is 1/4 x plus 3. So I'm going to start by doing f of g of x first. So I'm going to rewrite my f function with empty parentheses and then plug my g function in here. Simplify that out, so distribute the 4 and you're going to have x plus 12 minus 12. Simplify that farther and we get x. Now this one has potential because the first composition worked. You still have to do the second composition because sometimes one of the compositions will give you an x back, but the other one won't. So we still do need to do g of f of x. So now I rewrite my g function with an empty set of parentheses wherever I have that x, plug in the f function into my parentheses. So I'll have 4x minus 12 in here this time. Now distribute out that 1/4 and I'm going to have x minus 3 plus 3, which gives me just an x. So since both of my functions equaled x when I did the compositions, that means these are inverses of each other.